All right. Let's kind of do that. Room's always a little strange. Okay, recording. Okay, hi everyone. Welcome to the November C++ users group meeting. First off, I'd like to thank Microsoft for donating and sponsoring the room for us. I also want to thank Conan and JFrog for sponsoring our Meetup account. Let's see. One other announcement real quick. So we are looking at getting pizza going again. I'm kind of looking for somebody to help coordinate that. So in the past, when we've done that, we've had a person that coordinates the pizza sponsors. Is typically just working with recruiters and so forth. It's not a requirement to get that ramped up, but it'll help us get that going if somebody wants to help out with that. Let's see. Chris or anybody else, do you have anything you want to say on CPPCon?
Conference registration is open. Buy lots of tickets, bring your friends.
Okay, so CPPCon is first week of October this year?
Correct.
Okay.
The 6th week of September. It's always in September.
Don't do that. You're going to mess with my head way too much. And frankly, enough people have done that already. Okay, so with that, start our main presentation with Yu Quinn on solving the diamond problem. Thanks.
Okay, I will start. Let's talk about solve the diamond problem. I designed a new design pattern, which is called decoupling data interface from data implementation as a clean and a general solution to multiple inheritance. By clean, I mean this design pattern can solve the name clash very cleanly. By general, which means, okay, I started with C++, and also it's the main topic today. But this design pattern can also apply to other languages, including the languages with native multiple inheritance support, like DDIFI, Lisp, and Python. But it also can be applied to the so-called single inheritance language, Java, C#, D. Okay, I think this is Northwest. Everybody knows about D.
D is acceptable.
You can only say that when Walter's not here.
Actually, I said that. I first give this talk to Walter's D community to do it in how to do it in D. Actually, I submit to CPPCon. One of the reviewer comments, because he only saw my abstract, his comment is, what this guy is doing? The Java C# is single inheritance language. You claim you can achieve multiple inheritance there, so give me a very low score. Okay, I didn't get into CPCon, but I plan to appeal. Okay, if that's the process, okay, and I will show you. I know this is C++ meeting, but in the end, I will very briefly show how to do it in Java. You will get clean multiple inheritance in Java as it is. Okay, actually, with this design pattern, Microsoft and Oracle can rebrand their language as clean multiple inheritance languages. And before I start, okay, the key idea is about the data interface, not just the method interface. And I also want to mention that this work is patent pending. I don't want to mislead anybody. When I do the research on this problem, I found a patent from Microsoft about multiple inheritance. And I realized, well, my method is much better than theirs, so I should file a patent too. So I filed a patent. So this design pattern is patent pending. Talk outline. So I will first give a little bit intro about me, and then I will review how the multiple inheritance currently work in C++, and the diamond problem, why it is hard. Basically, in my view, First is because of the memory model to handle multiple inheritance. The secondly is what I call semantic branching. That is a concept I will introduce. And I will also talk about the current solution, what people currently do. I think most people using composition, which is better, slightly better than the native C++ multiple inheritance method. Then it's the main topic today, that is my data pattern, DDIFI. I will introduce the concept and the key ideas, and then we will walk through the code, the actual code in C++ to see how this is done. And then I will give a guideline, the general principle to achieve multiple inheritance with DDIFI in C++. And a very brief time, I will work through Java for single inheritance languages. Okay, and lastly is Q&A. A little bit about me. And so I did my PhD at Oxford University. My thesis advisor is Professor Tony Hall. I think if you don't know him, he wins the Turing Award for his contribution in programming languages. When I did PhD there, my thesis is about process algebra, communicating sequential process. I'm not sure how many of you know it, but that is what the Go language from Google based on. But unfortunately, my personal interest is not very so much into process algebra. I'm more interested in OOP, object-oriented programming. So after I did my PhD with Tony Hall, I decided to leave because I don't think it's my interest in process algebra. When I was in Oxford, I was mainly influenced by IFL, which is a early OOP languages. I think it appeared about the same time as C++, but unfortunately, I have to say, unfortunately, C++ wins the market. IFL actually is a very nice languages. After that, at some point, I joined Google. I came to States and joined Google. I was working in the tool department, software tooling department. And at that time, Google is a relatively small company. I think around 1,000 people or something. There are three main languages used in Google, which is C++ for backend, Java for frontend, and Python for the Glue code. I mean, it's not, I'd say Python is the king for machine learning, but at that time, it's just a Glue language. We have lots of trouble with C++ in backend. So the company is looking for alternatives. And I did some research, and I actually followed Walter Bright for some time. I know he's working on D, which is still pre-1.0. But I know the company is looking for alternatives. So I invited Walter Bright to Google, to California, to give a talk about his D. I think it's a well-received talk. But I checked with our EVP at then, Alan Eustace. He said the language is still in its early stage. They want to wait. They want to be more mature. But the company also has other plans. So, which is Go. I think it started in 2007 internally, and released in 2009, which is Go and based on CSV. I'm not involved in Go because I'm not interested in process algebra. After that, I was working for my own startup. I think some people who also worked on in startup, you always want to be more efficient than big companies. So you're always looking for some more advanced languages and tools. So that's why I'm still looking around for better languages. So that's a very brief introduction about me. Okay, let's start. So this is the overview of multiple inheritance. So historically, C++ don't have multiple inheritance in its first version. It started with the second version in 1989. But it caused a lot of headache. It's mainly because of the diamond problem, that's the main topic of this talk. For example, in Java, in Google, C++ coding style, we strongly advised against using multiple inheritance, mainly because of the diamond problem. And also, there's another evidence that is the later languages like Java, C#, and D, they all avoid multiple inheritance. They choose to use a single inheritance and multiple interfaces. The problem is that we still think multiple inheritance is very useful because you can reuse the code, not just the method interface. Okay. I mean, people start to using Java and C#, and then they realize that, okay, sometimes I need to pull in some code as implementation. Well, then people start to invent some other mechanisms. Okay, they avoid multiple inheritance, but they try to introduce some other languages, mechanisms, try to recover some of the functionality of multiple inheritance. And so in Scala PHP, it's called a trend. In Ruby, Dart, D, it's called a mix-in. However, both trend and mix-in share the same problem. I mean, if you really do this, eventually you will run to the name clash problem. Okay, you mix different mix-ins and then you have some clash, and you still have need to some ways to resolve it. So I don't think they are clean solution. Okay, my design pattern, DDIFI, solved this very cleanly, which I will show. It solved the name clash problem, and secondly, it's general. It applies to all these languages. Actually, on my GitHub repo, I have implementation in 9 languages. Okay, you can check and run it by yourself. Okay, the diamond problem. So this one is I copied from Wikipedia. The diamond problem is an ambiguity that arises when two classes, B and C, inherit from A, and D inherits both B and C. If there's a method in A that B, C have overridden, but D does not override it, then which version of the method does D inherit? Is that from B or from C? Okay. Actually, by this, firstly, I think this is not very good description of the problem, because it's only talking about the method. But actually, for the method clash, it's very easy to resolve. The answer is right in the problem description. It restricts that the D does not override. Why do you have such restriction in, I mean, practical engineering work? You can just override it. That's all. So, and if you want the method in B or C or even from A, you can use a fully quantified name. Okay, so method name clash in diamond problem it's not really a problem. Okay, it can be solved by the programmer easily. They call it problem. I think they want the compiler to help you to solve it, but no compiler can automatically solve this application semantics. issue. Okay, it's your application semantics. Okay, the program can solve it. So for method resolution, it's very easy. The more difficult problem is the fields, the data fields. Okay, which I will show, and which is the main problem I solved with my design pattern. So let's consider this problem. Let's model a university. Okay, so at the root of the class, you have person. A person has name and address as data field. And on the left-hand side, you have student. Student inherit from person. You have name and address. Okay, I'm showing a flattened view. So you inherit these two fields. On the right-hand side, you have faculty. And the faculty also inherit name and address. Okay. Now at the bottom, you have this research assistant, which inherit both student and faculty. Now, here's the problem. For each person, you can only have one name. One name. That field need to be joined. And then you can have two different addresses. One as student address, that's your dorm. You can take a rest. And the other is faculty address, where you do your bench work. So the ideal semantics of a research assistant is you should have exactly three fields. The name, one name that is joined, and the two different address. Okay, so this semantics is not directly doable in plain C++ multiple inheritance in its native mechanism. Okay, my design pattern can do it. So that's what I'm talking about. You want the name to be joined, and you want the address to be separated. As I said in this talk, I will mainly talking about how to resolve this field issue resolution. Before we do that, let's show how we do it in plain multiple inheritance in C++. Okay, C++ provide a mechanism which is called virtual inheritance. Okay, there's a regular inheritance, there's a virtual inheritance. The virtual inheritance is supposed to mean that if you declare you have a virtual inheritance, your fields will be joined. Okay, so I do a macro here. So this virtual can be either the keyword virtual or it can be empty. The empty, which means the regular inheritance. In virtual, if I define the virtual, it means the virtual inheritance. Okay, so this is just a very plain implementation. So for person, you have name, you have address. Student inherits from person, faculty from person, inherit from person, and the research assistant inherit from both student and faculty. Okay, then we define virtual as the keyword virtual. You end up in research assistant, you only have one name, and also the address will be joined. So you have two fields. If you define virtual as empty, which means regular inheritance in C++, you end up, you have two names and two addresses. So in total, 4 fields. But we know ideally we want only 3 fields. Okay, so this is not doable in plain C++ multiple inheritance. And the main problem with the C++ multiple inheritance problems is that the virtual mechanism can only be applied on a class as a whole. It does not provide a mechanism to treat each individual fields individually. I want the name to be shared. I want the fields. I want the address to be separated. Okay, that's the main problem with the C++ mechanism. Then let's check a little bit about C++ memory model, memory layout. This talk is not about a memory model. So this slide is the only slide that I talk about the layout because it's too messy. My conclusion is too messy to be worked on. The first diagram, okay, it's very small, but you don't have to read it in detail actually. On the top left, this one actually shows the diamond problem I just described from this Wikipedia page. Okay, so nothing fancy there. Just show you how this virtual table, how this fields, the layouts are. Okay, and this diagram on the right-hand side, it's showing some combination of regular inheritance and virtual inheritance. The solid line are regular, non-virtual inheritance. The dashed arrow is the virtual inheritance. Okay, so this is another problem of C++ native multiple inheritance mechanism. Okay, if in your inheritance lattice, okay, you have this all different kinds of combination of virtual and non-virtual. Your memory model is too complex to figure out. Okay. The third diagram on the low bottom left, it's the patent I'm talking about from Microsoft. I think they invented some mechanism in the compiler, C++ compiler to do it, and basically this is showing how they map the fields and how they do the virtual table kind of thing. Okay, it's very complex. I studied all this, and my conclusion is too messy. The main problem, okay, is here. I have a diagram here. On the top diagram is for single inheritance. For single inheritance, it's very easy. Why? Because suppose we are talking about the class J, okay, and we want to, eventually your compiler need to decide the specify very clearly what the memory layout it is. Okay, for single inheritance, you just tell them. You just tell A, C, J. That's it. Single inheritance. You just tie it piece by piece. That's done. But for the multiple inheritance, it's not a tree, it's a lattice. And for a node, a leaf node of the lattice, okay, there are multiple superclasses at the same level. And how would you arrange them linearly? Because eventually, when you map to the computer memory, it's linear. Okay, so basically it becomes how do you map a lattice into a linear layout? Okay, and then you confound with this virtual and non-virtual inheritance we are talking about. It's messy. I don't think it's doable. Okay, so after I studied all this material, I realized that's not the way to go. That we can do it, and especially we want to achieve that name to be shared and address to be separated. The second problem is what I call semantic branching. I want to explain it here. So in this inheritance diagram, the student inherits from person, but the semantics of its address field, this is the application semantics, is stored, which is different from the faculty, the address field in faculty, which is lab. So which means, okay, you inherit both from person, and this field name is called address, but it's the same name. But at this point, the semantics has branched. One is dorm, the other is lab. Okay, and in the research assistant, okay, if there's no special handling of this, you end up with you mixing two different semantics into one common name. That's the main problem. Okay, so that's what I call semantic branching. So for the field name, there's no semantic branching. Okay, it's just one name in all these four classes. But for the address, it branched. So we call the person as the semantic branching site of the field address. Okay, we'll use this concept later on for my data pattern, but I have to introduce it here. It's called semantic branching. Now, I will show what's the current engineering practice that is use composition instead of multiple inheritance and discuss its problem. Okay, so we know that if you use native multiple inheritance from C++, you have this diamond problem. So people try to avoid it. And the common practice is to use composition. Basically, you declare the sub-objects. You declare a student sub-objects and a faculty sub-objects, okay? And you only inherit the interface. It's like in Java. You only inherit the method interface, but not the method body, not the code, okay? And then you do this sub-objects, okay? The problem is, one is you have to manually forward. Okay, you have to manually forward because for this do bench work, you will forward this method call to the faculty object. And for this take rest, you will forward that call to the student method. So, sub objects. Okay, so for any non-trivial application, typically you have lots of non-trivial method. Okay, so for each of the method, you have to do this forwarding, manually forwarding. Okay, that's the first problem, which I think is some form of code duplication. Because I mean, ideally, suppose we don't have this diamond problem. If you use multiple inheritance, you inherit code. That's all. You don't have to do this manual forwarding. The problem two is about the data duplication. We just talking about the name, and basically you have name in both of the sub objects. Okay, when you read it and when you set it, you need to set to the both places. Okay, and then you run into some synchronization issue in multi-threaded environment. Okay, then you have to have some log. Okay, this complicated code. So it's also data duplication. So two main problems. Some form of code duplication, some form of data duplication. That the main problem is for use composition. Okay. From now, we're talking about how I solve this problem. Okay. So based on the problems we just discussed, the C+ memory model and the composition approach, okay, I realized the fields is causing us too much trouble. So I don't think it's fixable in the memory layout memory model by itself. So I think, can we just get rid of it? Then naturally the next question is, okay, that's fine, we can get rid of it. How would you implement a regular method? How would you implement a regular method? Oh, we know it's a common practice that for each of the fields, we will define getters and setters. That is called accessors or properties, depends on which language you're coming from. But anyway, then I realized, okay, we can use these accessors. And the most important thing I realized is that you declare this accessors as virtual method. You don't implement it. You don't include them. Okay, you only declare them as virtual accessors. Here is name and address. That's the property. That's a method. Okay, and then in your regular method, you can just use this name and address as you want in place of the raw fields. Okay, and in the implementation class, you actually have the fields definition and you implement the accessor. Okay, so that's what I call you decouple the data interface from the data implementation. And the nice thing about this is that you feel the problem go away. Okay, you can inherit anything because here you only deal with the virtual methods, virtual accessors. You don't deal with fields anymore because there's no fields inherited. Okay, so I do a comparison between how we come here. Okay, so firstly we have procedure programming. There you define struct person which has the data fields. And then you have a function, global function, which operate on this struct. Okay. When the object-oriented programming came, okay, we bundle them together. So you define a class, it has fields in it, and you have a method in it, and you call it on this object to access the raw fields. With OOP, with DDIFI, right, data pattern, what you do is you move your data field definition into a implementation class. And for the regular methods, instead of access the raw data fields, you call the virtual property method, getter and setter. And in the implementation class, you actually define the data fields and override the virtual getter and setter. Now we see how it works. I will show you the code very briefly. But before that, let's come to visit the semantic branching problem again. This problem solved the name clash on the shared fields. But for the field, the address in our example, which mean to be branch, okay, how would you do it? You have to name it properly. So in the let's go back to the inheritance diagram. Okay, in the research assistant objects, okay, we will name these two different accessor differently. One is called the student address, the other is the faculty address. Once you give it the correct name, okay, then you don't have that name cache problem. And to do it with DDIFI, which means in the student class, you will introduce a new property, getter or setter, which is called the student address. In the faculty, you will define a new property method, which is called the faculty address. Okay, now let's go to the code. This is how we do it with the C++. Okay, the first one is simple, person. So for person, you define virtual name, virtual address as the abstract property method. And in person implementation, you have these fields, the actual data fields defined, and you override this property methods. Okay. Now, let's talking about the inheritance. So faculty inherit from the person. Okay. At this point, that is what I call here. So immediately, just below your semantic branching site, introduce a new semantic assigning property. That is the address. Okay. So, but we need to give it a new name. We call it a lab. At this point, for faculty, you can just return address. No problem with that. Okay. And the key thing in your regular method implementation, that is do bench work. Okay. You have to use this new semantic assigning property. Because if you still use address, later on, when you go to the research assistant class, okay, which inherit this do bench work method, if you call address here, okay, we have talk about it. It has two meanings. One is from the faculty, the other from the student. It will mess up. Okay, so this is very important. You define a new semantic virtual property, and you have to use it here. Okay, then this do bench work will be inherited and behave correctly eventually in the research assistant class. For the faculty implementation, firstly, you inherit from the faculty, and then it's still possible to reuse the data which is here. That is person implementation, because this is a so simple class. I don't want to introduce anything new. So code reuse is still possible, a data reuse. So you just inherit from a person implementation. Symmetrically, we do it with student. The student inherit from person, and you add a new semantic assigning property, which is called DOM. And in the take rest method, you have to use this DOM, this new semantic property. And similarly, for the student implementation, you inherit from both student and the person implementation, which is you reuse your code. Now the key part, the research assistant. Okay, the research assistant inherit from student and from faculty. That's all. And in the implementation of research assistant, you define the exactly three data fields we're talking about. You have a single name, you have two different addresses, and you implement this virtual property. You override this virtual property to return the correct fields, one of either its name, faculty, or student address. That's all. So we write some simple application code and we run it. Okay, so we achieved that in this diamond inheritance, there's only one name field and two different address. It is achieved. Okay. So that's it. And based on this, actually, we can also have alternative implementation of research assistant. Suppose it's a biology research assistant. Okay, he need to do some bench work, and he want to develop some micronym, and which you may need to give it 24 to develop, and you need to alternate between lab A and lab B. Okay, so here to do this, you can choose to only have two different fields, that you have a name and you have a student address. But for the lab, okay, you can just use another. You can just define override the virtual property without define any fields at all. and you can use some computation to calculate what's the weekday, and you alternate between two labs. So the key point here is, let's go back to the inheritance. The key point here is that the data fields of the research assistant is totally independent from either student or faculty, even person. The data fields are totally independent. If you want, like what we do for the student implementation, it's still an option. You can inherit from a person implementation, but you are not required to do so. Okay, and in the research student implementation, we choose it to do it from scratch. We paint the memory layout. We design the memory layout by ourselves. Okay, so here we need 3 fields. We define 3 fields. That's it. For bio student, bio research student, 2 fields. I give you the 2 fields. Okay, there's no name clash. By using virtual property accessor, the problem solved. So that's my main design pattern. And the rest, a few slides, basically to formalize into the new programming rules. Okay, the first one is you split for any class you want to model, you split it into data interface and the data implementation. In the data interface, you define the abstract virtual property, and you define your regular methods using this virtual property. And for the data implementation class, you actually define the fields and override the virtual property to use these fields. For the subclassing, when you want to inherit a B from A, okay, then what you do is you override the virtual properties depending on your application semantics. And in the subclasses implementation, which is totally independent from the superclasses implementation, it's depending on your application semantics. It's still an option to do so, but you are not required to do so. And finally, what I call the semantic assigning property, which is I showed before. After there's a semantic branching, you must introduce a new semantic property after the branching, and then later on you override that new property. Don't mess up with the original the address because it's shared. That name is shared. With this, you can achieve field join and field separation as you want. I mean, depends on your application semantics. So the success of DDIFI depends on the method implementation without concrete field definition. If you read this, and if you know other languages, you will know this is what Java introduced in version 8. That is called the default method. Default method means you can, in the Java interface, you can have method body defined, but you are not allowed to have any fields. Then it naturally comes to the question, what do? You define virtual fields, you define virtual properties, then your default methods will work. And if you think again, this is multiple inheritance. And I will show you in Java. This is the multiple inheritance in Java. It's okay. So
Would it be possible to make the text a bit bigger?
I don't know how to do this. What's the shortcut?
Control scroll normally is what most apps use.
This is no.
Control.
Oh,
Yes. Okay.
Yes. Thank you.
Okay. Good enough? Okay. So, okay, first I have to say this is Java code, okay. So in the interface, you define virtual methods, virtual property methods, as we said, okay. And for this simple class, we don't have any methods, so that's fine. And for the implementation, the person implementation, you define the actual fields and you override the virtual property. For faculty inherit from a person, and we introduce new semantic assigning property. We discussed before, the lab, and which return address. The address is here, it's abstract, but just return. And then you can also do the regular methods definition. Okay, using this new semantic assigning property. In the faculty, oops. I can't double click.
I think you flipped tab.
You lost your tab there.
Yeah, your tab's on the left, I think.
No, it is.
Try going down just a half inch. No, that's about 12 inches. No, go, just move the mouse to the upper left. Don't scroll, move the mouse. Up, down, no. Down, up.
Hang on.
Where's my laser pointer?
That's my slides. That's
Oh.
I want to show my code.
Okay.
Let me see if I can find it.
It could have been not being on the white.
No, right. I think I have code in, on my local machine. Okay. But are you able to see how to increase the font size?
Under terminal? Oh, wait, no, under terminal, preferences,
Or how about view zoom?
and, no, I think it's under text and kick the font size out. Yep, there it is, font regular mono 14, change. Just kick it up to 18 or 24.
It's not
Go
working.
ahead and see if you can do it.
Sorry about that. Okay, I think let's just continue. So in the faculty, you define the new semantic property lab, and in the do bench work, you will call this new property method to do that. And for the implementation, you will just you first extend the person implementation, because we can just reuse it, and then you implement the faculty this interface which inherit. So from the person implementation, you inherit the actual data fields. From this faculty, you inherit the code, the method implementation. So both fields and the method are inherited here. You do the same for the student. It's a semantic student. You introduce a new semantic property called DOM, and in the take rest method, you call storm, this new semantic property. And for the student implementation, you pull in the data fields from person implementation, and you pull in the method implementation from student, from this interface, the default methods. Okay, and finally, the research for the research assistant, you extend the interface, Java interface, from both student and the faculty. And here, actually, you pull in the method implementation already. Okay, in the research assistant implementation, again, you actually define the three fields, and you override the virtual property to make use these three fields. That's all. So with this, you achieved clean multiple inheritance in Java. So which means it's doable. And we know that C. We know that C# mostly mapped its language features from Java. So 5 years later, also in version 8.0, it introduced the default methods. Okay, which means what we just described also can be applied in C#. So now that's what I'm saying. So now with my design pattern DDIFI, Oracle and Microsoft can rebrand their languages as multiple inheritance languages, and it's clean multiple inheritance languages. Okay, in retrospect, after I designed this pattern, I realized all the languages mechanism to support my design pattern is available when the first version of multiple inheritance is introduced into C++ in 1989. So I did some research and I did find it. Oh, sorry, I think okay, I see here, great. So actually I found the code. This is the source code of the C++ 2.0. Okay, the only problem is, okay, it uses the ancient syntax, which I cannot fix. I'm not a compiler guy. Okay, if someone knows, I mean, the old C and C++ syntax and can fix its compiler, so I have a challenge here. So please send me a PR. I want to say my design pattern works with the first version of C++ that introduced multiple inheritance. As I said, I first gave this talk to the D community, and I also showed how this can be done in D, because D mostly follows Java. Okay, so we discussed the pros and cons of my approach. The pros is, as I said, it's clean. It completely solved the diamond problem. The field, how do you handle the name clash of the fields cleanly? Okay, and secondly, it's general. It works in a number of languages I have described. Okay, the cons. The cons is that firstly, each class now you have to split into two different classes. One is called the data interface. The other is called the data implementation. This complex you design, but I think in any serious industry software, we do that already. You separate the interface and the implementation already. So that's not a big problem for the working programmer. And the second thing I can think of is that my design pattern, for my design pattern to work, it heavily use the virtual property, which means every field access is a virtual function call. Okay, this will incur some penalty, performance penalty. My rebuttal will be that, firstly, virtual function is as ancient as inheritance itself. It's object-oriented programming itself. So it's heavily optimized by the modern compilers. Okay, and if you don't want to use virtual maximum, you probably don't want to use OOP. So I don't think that's a big problem. Okay, and also in the implementation, you can still use a local temporary variable. Your temporary variable, you read it, okay, and you use it to do your calculation, and finally you write it back. Then you reduce your virtual property call. So that's it. So the general guideline is you try to define everything as virtual, and you only in your implementation you actually define the fields to do it. I want to make another for my data pattern. So the fields are like the legs of a table, and on top of these legs of these fields, okay, you can build applications with functionalities. In this case, you can put plants on top of it. But in certain scenarios, okay, these legs cause you too much trouble. Okay, so what do? You get rid of those solid legs. Okay, instead you use the virtual legs. The virtual legs in this video is the string. It's a string. Okay, because the string is more flexible than the solid legs to handle. So with video playing, I will take questions. That's the end of my talk.
Can I go back and see the slide about the final version of student?
I think research assistant.
No, student.
Student, C++ code, right?
Yes.
Student, right here.
Okay.
You define the new semantic.
Well, no, I'm checking the hierarchy on
Right.
student.
No problem.
So student. One thing I potentially don't like about this is when you implement student impl, you have to know that student derives from person impl. Wouldn't it be better to have an empty impl layer that directly inherits from person impl that had some alias name that was associated with student?
As I said, it's an option. It's an option. You can even totally get rid of this and define your fields, your own field here. The key thing is it's still an option. It's an option to do so. I chose it to do this way because, okay, I implemented the person implementation already. There's not any other extra functionality I needed, so I just reuse the code. If you choose, if your application, for your application semantics, you want something different, you want something fancy, something special, you can do it here.
Right. Now, something I wanted to check about here also, just make sure I understood. Your student impl, if somebody wanted to use a student by itself, they would actually have to say student impl?
Yes.
As opposed to calling it just a student? Normally you try and hide, you name the object what it is and you hide the impl and data pairing internal to it.
Yeah, that's, okay, I forgot to mention, actually, that's called the factor method. Which means with my data pattern, when you create a new object, you use a factory method. The factory method will, like in this case, you create a research assistant implementation class and you return it as a research student. Yeah, you have the factory method. You cannot directly new a student. That won't work. But with this, you need a factory method. That's why.
Okay, you're going to get some pushback resistance on that. I'm not against factory methods. I've done a lot of several talks on
I actually like that.
design patterns. Well, and actually, I heavily used them in some vaporware, or not, without vaporware, but I did some. The forbidden term of virtual constructor, yes, I did it. But,
And
so,
you admit to it?
yeah, it was black magic. It was also an implementation of reflection in old C++. But one other thing I wanted to check to make sure that it was still plausible, even if you have a factory created, that you can take your research assistant and directly cast that to a student or to a person.
Yeah, that I did here. I cast it. I assign it.
Okay.
Yeah, I'm using the factory method to create this object, and then I assign it to faculty. I assign it to student. That's no problem.
And it works because it inherited the virtual table. And it's actually pointing at the derived implementation of the virtual table.
Yeah, so. That's right. I still keep the same inheritance hierarchy. Right. I only separate the implementation.
But okay.
If no.
Yeah, the one trick is a rule. I'm not sure if you mentioned this, but it might be an additional. Your implementation side cannot add any virtuals. Correct?
Yeah, but it's application semantics.
Yeah.
I mean, actually, in one of my rules, I specify that. I mean, for the private method, method, you can do it in the implementation class. For the public method, you do it in the data interface class because it is intended to be inherited. But for the private method, you do it in the implementation class.
I have another twist you might consider on this. You publicly inherit your interface, privately inherit your data interface or your data implementation. That way, further derived classes don't see that; they only see your interface.
Yeah, that's you can do that.
Yeah. There's some promise to it. It creates a diamond mirrored interface in front of it with shadow data behind it.
Yeah, exactly.
But you've gone from a diamond, a two-dimensional complex thing to a three-dimensional where it's a cube.
But
well, it's not the diamond, but each node in the diamond has its own set of data.
Yeah, that's exactly right. But you have to consider trade-off. If you want to solve it, at least my approach cleanly solved it. Okay, cleanly solved it. You have to consider the trade-off.
Yeah.
But yes, I have a shadow. Exactly. On the top of it is your proper inheritance hierarchy that you want. In the bottom is the actual implementation. But with this structure, I did this cleanly. I cleanly solved the diamond problem.
Yeah.
C# guy by day, so I've mostly just figured out how to work without.
You can check my GitHub repo. I have a C# implementation.
Yeah.
So as I said, from now on, they can claim the C# is a multiple inheritance language.
I live in a world where I get to define most of my stuff, so if I ever see that, it's time to change my architecture. But granted, there's cases where you just simply can't because of what you gotta use.
Well, I've used multiple inheritance and end up with the diamond problem on multiple different times. And there's, some tricks to get around some of it. Yeah, one potential, you have accessors for all of your data.
Yes.
I have a separate issue with the term accessors or the implementation of accessors. But if you just had a lab assistant or whatever you called the final derived object, and you wanted an address to the name, there's no way you could somehow get at the address to that name unless you provided an access that returned an address. So, I mean, you couldn't interchangeably use that.
You don't, I know C++ is a raw language. You can take the address of a pointer. Okay. With this method, you don't want to do that.
We
won't do
wouldn't.
that. Yeah.
Yeah.
You do everything through the virtual property method.
Yeah.
Yeah.
The other slight issue on it is, and you actually showed one of it in, when you had different methods that faculty would do versus students, and you had the lab assistant do one that was kind of a combined. Now actually go down several slides.
Okay. This is student.
Yeah, okay, there's one. There was take rest.
Take rest. Yeah. So you can you take rest in your dorm and you
really in most good, what I consider good design, which is very subjective and it depends on your frame of reference. Take rest is a perfect example of most classes shouldn't actually expose the internals of what the data is there. When you called student and you said take rest, it wouldn't matter, what the implementation of student was, which you were able to abstract off here, other than your student knew that it had a dorm room to go take its rest in.
Okay.
Yeah. But the concept of exposing address I don't think accessor should be necessarily one-to-one with what your internal data is, because people are going to get used to using get address or set address. And then when you go to change your implementation of what the address is, now all of a sudden you have an address that requires a city and state and zip code in addition to the street. That changed the internal implementation. It changes your interface. Everybody down from there knows what your internal data is different. There should be potentially a set address where it's passed in a complex field that it parses and it stores it in, street, city. So that's why I don't like accessors. It exposes your internal implementation if every piece of data has a get set on it. Many times those things are combination values that a method should set what they are, as opposed to you don't change the city address or the street address and then change the city and then change the state and then change the zip code in 4 separate calls.
right.
Am I making myself clear on that? Yeah.
I'm using this example only to show that how would you solve the name tag on the fields.
Right.
Okay.
So
So
you basically aliased variable names by using function names. Yeah. Yeah.
and that's the trick.
For your example. Yeah.
Yeah. That's the trick that you can do this cleaning, because for the methods, it's very easy with the current language mechanism, because I don't want to change the compiler to do it, to resolve it. Okay. For the fields, there's no way. There's no way. So I have to hide the fields down below into the implementation class. And on top of it, if you want to do something with actual fields, you have to use the property method. That's the trick. That's the trick you need to solve this problem.
I got a question for you. We've introduced a bunch of function aliases and virtual methods. In most code, it's not a big deal for performance.
Right.
Some code it is. Do you have a feel for, in a practical sense, how this impacts the performance of real?
Right. That you have to measure it. I don't have any figure.
Yeah, I was just thinking it's like, I'm almost wondering if if this was implemented as templates, then you'd get away from that. But I'm not a template guy super deep, so it's like, it sounds like a thing to do. How you would actually do it, I'm not sure.
It could be done.
I think it could be done. It's just not intuitive to me off the top of my head how to do it, because I don't do templates every day. But I'm thinking there might be a template implementation that would kind of take this one more level further and let the compiler handle a lot of.
There are a lot of people who make their living by saying virtual is evil.
Oh, I know.
It's not true.
No.
And especially C people like saying that with a pointer to function. But yeah, hey,
It's the right tool for.
well, except for okay. A virtual implementation does cause one layer of indirection, which is almost just one assembly instruction anymore because it's built to handle that.
Yeah.
But it is faster than any other alternative. If you have a switch statement that figures out which function you're calling, and then therefore you call the right, pointer to function type mechanism, that is like 12 steps and going to be 100 times. And you have to set it up manually every single time, which is error prone.
And the cost to the processor for getting the branch prediction wrong is way higher than a virtual.
Well, actually, you can have branch prediction error with polymorphism also.
You can.
But direct. Yeah. And there's people that also claim, well, you're calling code that might not be local. You're calling, you're going to cause a cache hit. You're going to cause a load. You're going to have the same problem with that in any language. And it only ever happens the very first time. And then after, it's really fast.
That is,
Yeah.
from a, for a lot of code, it doesn't matter.
Yeah.
Some code, it really does.
Well, then just don't use this.
And, well, no, I mean, that's what I'm trying to get at, is what's the practical hit so we know when to use it? Because it could be, in some cases, the compiler can optimize some of this out as well. And so it's entirely possible that in certain scenarios, the hit is zero. And that, of course, that takes you to templates where you could say the hit is zero because it's, compile time. But I was just trying to, get a feel for, where are we at in that space?
Yeah, and I think he mentioned he didn't lay out the specifics of it, but he did.
Yeah.
There was a,
Oh, no.
my response is.
Yeah, that won't even tell you,
The
no.
compilers
Your
will
answer is,
optimize
you gotta
that.
benchmark it, that's.
You'll have to.
Yeah.
Yeah, that's, I was just wondering if you'd done that yet, so.
No.
Okay.
Well, actually, if you can throw the student example back up, I want to see how much of it is actually virtual. Because the virtual is only in the,
It's on the, it's
just
the data.
It's
access.
only on data.
right, so
Data.
it's only on the data accessor. And so that overrides the base
And you got-
implementation.
And you've got two issues there. One, it's on the data accessor.
Well, you
Okay, so
could,
you're calling a function instead of a direct data. And two,
with
it's
address,
virtualized, so it's almost like two levels of hit. But if the compiler is gonna inline and do a few other of its little magic tricks, it might go to zero, I don't know.
It might go to 1.
It might go to 1.
okay, now can we go up one
It might
slide
go to
and
an
see
nasty
person?
cache miss, but that's not a big deal. It's, you don't know until you really measure it, and probably even then it's gonna be situation specific. And my other, the other comment is that the very last slide, the little inverted thing, is that something standard? Did you make that up?
No, it's real.
No, you can
I've
go
seen
buy
those
those.
before.
But it's like, okay.
There's transparent strings you can't see from,
Like fish.
Yeah.
that holding this, and then there's two others that hold it from.
No, I'm just saying, when I saw how the thing was set up and the.
Oh, I didn't make this video. This video is, I downloaded from somewhere.
Okay.
So
Whoever
somebody else.
came up with that, that's clever. That's really cool.
Yeah.
There's 100 examples of
You
that
can
on
find them, they're
YouTube.
really cool.
Okay, it's the first.
And
time.
people make them really big, make like towers doing this.
Yeah.
Interesting.
Yeah,
Yes, I saw.
Yeah, that's clever.
It was like a table you would eat on,
that's pretty good.
like a whole, yeah. That's nuts.
You can use that for your standing desk, right?
That looks a little unstable.
Yeah, what could possibly go
If
wrong?
I have a problem to solve and I'm working on coding and I know, I know I need to implement this class and I want to have X as a base class and Y, and I go, I do some research and I find out in the library that here's X, which I need, and here's Y, which I need. And with traditional multiple inheritance, okay, I do the things that you've described that you're working to replace. But now, at least that way, I have to decide if each of these is public or private.
Right.
Okay, but I don't have to think at all about the implementation, at all.
Yeah.
Okay.
Yeah.
Now, I have to provide the implementation.
Yeah.
So now I have to understand X in this library, and I have to understand class Y in this library. I have to understand both of them well enough to provide the implementation behind the scenes and get it right. And of course, I'm always going to be in a hurry and it's going to be busy, and I'm probably not going to take as much time as I should have. And so now there's a chance I'm going to screw up the implementation, despite the fact that I kind of quickly read the documentation for X and Y.
Right.
And this could be a drawback. It's one thing if you're writing your own code, but it's another thing if you're trying to use library code with more complex classes.
I understand. As I said, it's a trade-off. Because the other approach is you run into the risk of name clash.
Well, yes.
When you have name clash, you still need to check the library code. Where's my clashes, and I want to resolve it. Okay. With my approach, okay, you avoid the name clash, but you need to know how do you want to lay out your exact fields. But and as I said, it's trade-off.
It's a trade-off.
Yeah.
But you
either
potentially
take the
have to
risk,
provide implementation for somebody else's code.
Yeah. But that's a but. But it's a trade-off. But my approach solve it cleanly. If you really run into the name clash problem in the library code, you can't solve it. That's the main difference. It is a trade-off. But if you really run into it, like as I said, you have a field in A and in B, and they are the exact same name. You want to keep some field to be joined, some field to be separated. You won't be able to do it. You won't be able to do it. At least my approach will solve it.
It solves that problem.
Yeah. So it depends. It depends on your usage. If you really run into the problem I described, and you want to solve it cleanly, you have to use my pattern.
Yeah.
We have about 10 minutes left, folks, before we have to get out of here, so.
But it's not like just if you run into the problem though, right? Because it's if consumers of you as the library author run into your problem, then you have to rewrite your library to support them inheriting your classes this way.
At
At least that's I think kind of what you're saying is like if like you want X and you want Y, but if they're not built to do this.
Implementation is not hidden away. You now have to provide it, and you have to understand enough to know how to provide it.
Right.
Yeah, that's right.
And somebody who uses you,
Yeah, that's right. That's right.
faces
Nothing like you can't just kind of decide it if you're trying to use classes that you didn't write.
Yeah, you have to know
You have to have the
layout, where it's coming from. Where exactly the field is defined.
And you have to own all the classes between you and that collision, basically.
Yeah, but as I said, you still have that in the implementation class is still an option to either make use of existing code or define your own layout. So.
Okay, any other questions? I'm gonna stop the video and you guys can keep chatting for another 10 minutes.
Saying I want to appeal for the report. I mean, because in the process